Hello everyone, this is Dr. E, and for today we're going to be working on mathematical systems in our lesson on geometry. And just like what I often tell my students, learning mathematics is like learning a new language. And for today, we're going to be encountering words that are a little bit too foreign for us, but knowing how or what the meaning of these words associated in some problems and lessons in geometry, we'll be able to understand the language of mathematics even better. So let's start with the definition of geometry. And by definition, geometry or the word geometry comes from the Greek language and it means to measure the earth. And that is how we define geometry using a definition similar to this one. And what we're going to be using would be reasoning and using logic to be able to understand patterns in mathematical problems similar to what we encounter in geometry. So we need to learn how to use reason and logic in order to recognize patterns, make conjectures, and develop the laws of this system. So there are several words here that we don't normally use, like conjectures and laws, and there's even laws in mathematics. And that is what we're going to be understanding and learning in today's lesson. And we're going to start with testing our logical thinking skill using patterns like this. So we're going to predict the next pattern that we're going to have given the sequence of figures that we are seeing here. So there's no mathematical operations, there's no mathematical formula that we are using, but we'll be able to figure out a way on how to draw the succeeding figure out of this sequence that we have here by logical thinking. And how are we going to use our logic? So by observing patterns. So we know that we have a quadrilateral here with a little triangle at the corner in this side of the square or quadrilateral. We don't know if this is really a square. And then the next square or next figure that we are seeing is that it has a little triangle right here in this corner. And the next pattern that we are seeing from this four-figured shape is that the triangle is now moved in this corner of this figure. So what do you think would be the next figure based on the sequence that we have? We know using logical reasoning that most likely the triangle or the corner of this quadrilateral will have this little triangle in this figure or in this sequence. And this is indeed the figure that we are seeing, and using logical thinking, we're able to recognize patterns. And this is one way on how we answer mathematical problems when there's no formula or formal procedures involved in our work. So let's say we have a sequence of numbers similar to this one. We have 2, 10, 50, 250. And what do you think is the number after 250? And just like what we did, we're going to be using patterns and logical thinking to be able to understand and predict the number that we are looking for. So from 2 to 10, how do you think we're able to move, or how does this number grew from 2 to 10? We know that maybe we are multiplying by 5. And if we multiply by 5, we know that it's equal to 10. That's why we have 10 after 2. Now, does this assumption also apply to 50? Let's check. If we multiply 5 to 10, which is also equal to 50, so that means that our assumption is somehow correct. So if we do this from 50 to 250, so that means if we multiply 50 by 5, it will equal to 250, which is still correct. And using the pattern that we are recognizing now using logical thinking, the next number that we're going to have is a number multiplied by 5, which is in this case 250, that is equal to 1250. 250. So this is how we use logical reasoning by observing patterns to be able to answer mathematical problems similar to what we just had on the two examples. And this particular thinking or way of thinking or reasoning is what we call as inductive reasoning in geometry. Now, moving to more systematic ways on how we would use logical thinking in geometry, we call systems or way on how we articulate statements in mathematics as axiomatic system or postulate system. And this is a system made up of undefined terms, defined terms, axioms or postulates, and theorems. So this is what we call as axiomatic system, also known as mathematical system, which are used in proving logical conclusion in geometry. So we are using logic in any conclusion that we are arriving in mathematics. So how are we going to make a more systematic approach on how we think mathematically? Let's start with undefined terms. And by definition, in a mathematical system, undefined terms, which is most basic terms that we don't need or we do not formally define but have meaning that we agreed upon. And some of these undefined terms are points, line, and plane, which means even if we don't have a formal definition of what point is, what a line is, and what a plane is, we already have an idea of what it means due to the past experiences that we had and how we use these words in actual problems that we encountered in our normal lives. Now, what about defined terms? Defined terms, of course, now that we have undefined terms, we can define it and we use undefined terms or already defined terms to formally define them, and we call this defined terms. I know that the meaning is a little bit wordy with so many undefined and defined words in the mix, but we know that if we're going to define line using geometry, because we can define line in a lot of ways, falling in line or line of sight. But in mathematics, the definition of a line is made up of set of points which is extended in opposite directions infinitely. So this is what defined terms are. And to give you a better visual of what it means is, if we're going to follow the definitions, it says it is a line that's made out of a set of points that is extended in opposite directions infinitely. So it could go right in this direction or this direction. And since it's infinite, we can write an arrow to the left and to the right, and we can even connect all these dots. And now we're seeing a line. So that is basically how we defined line in geometry based on the observation that we are seeing in lines. And the next one that we are going to be working on in a mathematical system is what we call as the axiom, which is quite a big word for most of us. An axiom is just an improved but agreed upon assumptions which applies to math in general. So what are these axioms? An example of this is if equals are added to equals, then the sums are equal. So let's say x is equal to 20 and y is equal to 30. If we have x plus y is equal to 30. So mathematically, we're able to come up with an axiom or an agreed upon assumption that x plus y is equal to 30 because x we set is 20 and y is equal to 30. So this is not always going to be true because we don't know what x and y is depending on how we define them. That's why we're only calling it an axiom, and this is specific in math in general. Now, what about postulates? So postulate is similar to axiom, but the only difference is that postulates are more specific to geometric statements. So it is an unproved but agreed upon assumption which applies to specific discipline which is in this case geometry. So an example of a postulate is that exactly one line can be drawn between 2 points, and this is always true in geometry because if we have 2 points and we connect those dots, we'll have a line. So if we have point A and point B, and if we connect those points, we have a line segment AB, and this is an example of a postulate because it's an agreed upon assumption that is specific to geometry. So if we're going to use this postulate, which states that if we are given any 2 points, and if we connect them, we'll create a line, and we have a line here. It may not be too straight, but we know that that will create a line, and that is basically what we call as postulate in mathematics because it's an agreed upon assumption specific to geometry. And the last one that we're going to be using in a mathematical system is we call as the theorem, and we are all familiar with the theorem, and I'm sure you can give me examples of a mathematical theorem that you have heard or learned from the past. So by definition, a statement which has been proved on the basis of other theorems, postulates, and or axioms is what we call as theorem. So example of a theorem is that if we have triangle ABC and it is a right triangle, then a squared plus b squared is equal to c squared is true. And we know that this particular formula in mathematics is something that we are more familiar with, and this is the Pythagorean theorem. So if we have a right triangle, and if we need to measure a missing side of a right triangle, we can use this formula to be able to figure out that missing triangle or verify its lengths. So this is how we think mathematically, also known as a mathematical system. So we'd be able to come up with more theorems and even postulates and axioms based on these definitions that we are using or words that we are using in mathematics. So let's use this way of thinking to be able to verify this statement if it's true or false. So according to this statement, the angles are complementary, or these angles are complementary. That means this angle and this angle, if we add them up, it will equal to 90 degrees. Now, can we say with confidence that what we are seeing here is indeed a complementary angles? And the answer here is no. It's a no because we can't really tell for sure or certain that this angle right here is a 90-degree angle because there's no labels or information that will tell us that it is indeed a 90-degree angle. Unless you have a protractor that you can use or any device that could measure angles, then we can say that this is indeed a complementary angle. But if we have a figure similar to this one, we can confidently say that angle 1 and angle 2, it's a complementary angle because this particular symbol is an agreed upon symbol in mathematics, which is could be a postulate or an axiom, that this is a 90-degree angle. So that means we can say that this is indeed a complementary or set of complementary angles because we are seeing an agreed upon notation of a 90-degree angle. So that is why it's important that we know all these terms, notations, symbols in mathematics to be able to confidently verify if our statement is true. Take another example with this statement. What we are seeing, according to the assumption, is that these segments have equal lengths. And we know that by just looking at the segment, without using a ruler, we really cannot tell if these two line segments have the same measurement. So we can say that no, we really cannot conclude or make a conclusion that what we are seeing are two line segments with equal lengths. But if there is a label, specifically a 1-inch measurement for line 1 and line 2, now we can verify that this is indeed two segments with equal lengths. So that's why we need to make sure that when we are making conclusion, we are basing it from facts or some agreed upon axioms or postulates to be able to understand or to be able to confidently conclude that our argument is true. And seeing another quadrilateral or a four-cornered figure, can we say that this figure is a square? Just like what the previous examples have taught us, we need to make sure that we are seeing labels and evidences that will tell us that this is indeed a square. And right now, we really cannot say if this is a square because it could be a rectangle, it could be a rhombus, or it could be a square, but we really cannot say for certain because there's no label, notations, or symbols that will tell us that this is an example of a geometrically defined square. And what is the definition of a square in geometry? A square has four right angles and four sides of equal lengths. And right now, we're just seeing a four-sided figure, but we cannot say if it's right angle or these sides are congruent. However, if we have a figure similar to what we are seeing right now, we can verify that this is indeed a square because we are seeing that our angles are all 90 degrees and their lines are all congruent. So this is how we think and use our logical thinking when we are working with geometry problems. And for your Numberbender challenge for today, given the figure right here that you are seeing, can you conclude that this statement is correct? And what is the statement? That the angles in this triangle have the same measure. So write down your answer and tell me if you can verify if this is a true or a false statement, and tell me why using the mathematical system that we have learned today. And this is our lesson on system or mathematical system, which is basically how we think logically by looking at the patterns that we are seeing in most math problems. Don't get too intimidated with big words in mathematics, just like what I've mentioned from our first second. Mathematics or learning mathematics is like learning a foreign language. You need to learn how to read it, say it, and write it to be able to understand and appreciate mathematics better. This is Dr. E, and see you again next time. Bye!